How does PID reduce oscillations without slowing response? Imagine trying to keep a ball balanced on a moving platform. If you push too hard or too softly, the ball wobbles or takes too long to settle. That's similar to how control systems work when managing processes. Now, a PID controller is like a smart hand that helps keep everything steady without making the system sluggish. But how does it do that? Let's break it down. First, the proportional part of the PID looks at how far off the system is from the target. It responds quickly by pushing back proportionally to the error. If the error is big, it pushes hard. If small, it pushes gently. This speeds up the response, making the system react fast. But if you turn this up too high, it can cause the system to oscillate or bounce around the set point. So, it needs to be just right. Next comes the integral part. It adds up all the past errors over time. This helps fix any steady mistakes, like if the system keeps drifting away from the target. The integral ensures the system reaches the exact set point and stays there. However, if the integral gain is too high, it can cause the system to overshoot or oscillate because it reacts to accumulated errors too aggressively. The derivative part is like a warning system that predicts what's coming next. It looks at how fast the error is changing. If the error is increasing rapidly, the derivative acts like a brake, slowing things down before oscillations get out of control. It dampens the system's response, preventing overshoot and bouncing. But if the derivative gain is too high, it can make the system overly sensitive to noise, causing unnecessary fluctuations. The trick is to tune all three parts carefully. Engineers often use methods like the Ziegler-Nichols or Cohen-Kuhn tuning techniques to find the perfect balance. They set the proportional gain high enough to get a quick response, but not so high that it causes oscillations. They adjust the integral gain to eliminate steady errors without making the system unstable. And they set the derivative gain to smooth out rapid changes, reducing overshoot and oscillations. In real-world applications like controlling motor speeds, temperature, or automated processes, this tuning allows the system to reach the desired point quickly and stay there steadily. Sometimes, filtering techniques are used to reduce sensor noise, which helps the derivative part work better without causing extra oscillations. So, by balancing these three gains, a PID controller can keep the system stable and responsive at the same time. The proportional part speeds things up, the integral removes steady errors, and the derivative dampens oscillations. Together, they make a control system that's both fast and steady, without the bouncing or sluggishness that can happen if one part is overdone.